Hello, welcome back to my YouTube channel. In this video we're gonna see how we should solve this following integral, improper integral from 0 to infinity of root x minus 1 over x plus 1 ln x dx. So this integral is a little bit more complicated and it extends to some things that you might not already know, but we're gonna use Feynman's technique to solve this problem. What does Feynman's trick say? It says that if you have a function like this, I can parameterize it and call it I of t, the integral from 0 to infinity of x to the t minus 1 over x plus 1 squared ln x dx. So this integral is parameterized now, and if I plug in x of half here, I'm going to get integral from 0 to infinity of x to the half minus 1 over x plus 1 squared ln x dx, which is the same thing as this one here. So Feynman's technique says that we should take the derivative of both sides of this equation to integrate the inside of the integral. So when my derivative moves inside the integral, it's going to become partial derivative, so it's going to be partial t. I'm taking the derivative of the both sides with respect to t. X to the t minus 1 over x plus 1 squared ln x dx. Thus, I prime of t is integral from 0 to infinity of x to the t ln x, because we are differentiating x to the t with respect to t. It's going to be an exponential function's derivative, which is given as the function multiplied by the ln of the base, x plus 1 squared ln x dx. So these ln x's are gonna cancel out, and that is making our work more simpler, because the ln x was the problem here in the denominator. So I prime of t is going to be the integral from 0 to infinity of x to the t of x plus 1 squared dx. What I'm going to do now is I'm going to define u to be x over x plus 1 and x to be u over 1 minus u. So the dx, according to the quotient rule, it's going to be 1 over 1 minus u squared du. So if I substitute my values here into the integral, my I prime of t is going to be integral from 0 to infinity. No, I got to change my bounds here. Oh yeah, so this is for the other part of the problem. Never mind. I'm going to write it as u over 1 minus u to the t over 1 over 1 minus u squared times 1 over 1 minus u squared du. And I can simplify this integral a little bit more. 1 over 1 minus u squared du. These two powers are gonna be canceling out again, which is gonna make our work a lot simpler again. So the integral from 0 to infinity of u over 1 minus u to the t du. Now I can write I prime of t as the integral from 0 to infinity of u to the t times 1 minus u to the power of negative t du. So I apologize, I should have changed the bounds of this integral to 1. I just forgot. The minute I stopped to tell you something, that was actually, I told you that, never mind, I meant to change the bound of this integral to the 1, because if u is defined by this, we should change our bounds of this integral from 0 to infinity to a proper bounds for this u substitution. And if infinity is because infinity is a concept, a very large number over a very large number plus 1 is somehow that very large number over that large number, which is 1, which is how we got our 1 here in this integral. So the moment I paused, I doubted that whether I changed my bound or not. That's why I said this integral is a little bit tricky. It has a lot of substitution and bounds changing. So this is my integral here. Can we proceed further now? Yeah, we can. If you take a closer look here, you might recall beta function, which is defined as integral from 0 to 1 over 1 minus y, a minus y times b minus y dy. The powers are not our concern here, just the bases. The bases match exactly the form that we want. So I'm just gonna recall one more thing, that beta function is defined as the gamma of a, the gamma function of a multiplied by gamma of b divided by gamma of a plus b. And another property of gamma function is that if I have gamma of a plus 1, I can write it as a gamma of a, which is a factorial. Now, my I prime of t, my integral, is the same as beta of t plus 1 and 1 minus t. You can substitute the powers here to see that this indeed results and yields in our integral here. I'm not going to do it, so I'll just leave it for you. If I write it in terms of the gamma function, it's going to yield t gamma of t plus 1 times gamma of 1 minus t divided by gamma of 2. Gamma of 2 can be written as gamma of 1 plus 1, which can be written as 1 gamma of 1, which can be written as 1 factorial, which I'm going to write just 1 factorial here in the denominator, which I prime of t is this. And gamma of t plus 1 can also be simplified to t to so here is a little bit trickier. T gamma of t, yes, t gamma of t. So I can write it as t gamma of t, gamma of 1 minus t over 1 factorial here. Thus, my I prime of t here is, so can we proceed further? Yeah. The gamma of t times gamma of 1 minus t is defined as pi divided by sine pi t. And if I substitute it back here, I'm going to get pi t over sine pi t. This is my I prime of t. Now I can integrate this function again to get rid of my I prime of t and actually get the results that I want. So I want to integrate it from 0 to half, because that was our initial bound of pi t over sine pi t dt. Let me see if so pi t divided by sine pi t dt. Now I'm going to do another substitution here. I'm going to say 2x equals pi t, 2 dx equals pi dt. Now my dx equals pi over 2 dt. What I'm going to do next, I'm going to multiply both sides by pi over 2 multiplied by 2 over pi t over sine pi t dt. And then I can plug and collect the pi over 2 dt as dx. And then I can I gotta do something about this. Oh, okay. So, and then I can collect sine pi t as sine 2x, which eventually it's gonna yield I of t to be integral from 0 to half of, if you do all the work, it's gonna be 2x over sine 2x dx. I can use the trigonometric identities of sine 2x as 2 sine x cosine of x, and then I can write this whole thing as 2 sine x cosine x dx. As you might notice, the 2's are going to cancel out perfectly here. And my I prime of t is 0 to half of x over sine x cosine x dx. Next, what I'm going to do is a little bit making it work more tricky here. Oops, I forgot this 2 over pi. I should have gotten it out of the integral. So I'm going to write it again. My I of t is 2 over pi, 0 to half of x over sine x cosine x dx. Now, the next step here is to multiply and divide the inner integral by secant squared x, aka 1 over cosine squared x. Oops, sine x. Secant squared x dx. Sine x cosine x times 1 over cosine squared x is just going to be sine x over cosine x, which is tan x. Thus, the I of t of mine that I'm looking for is simply x secant squared x over tan x dx. Now, if I do define my u as tan x, my du is going to be secant squared x dx. And my bounds, if I change them, are gonna be pi over going to be from 0 to pi over 4. Thus, I of t is 2 over pi from 0 to pi over 4 if you do all this bound changing here, because we gotta keep an eye out on the bound changings. I almost made a mistake in the previous bound changing, but if you just be careful, you would evade those kind of mistakes. So now, where were we? If I do all the substitutions here, and if I take arctan of both sides of this equation, I'm gonna get arctan of tan x, which is yielding arctan of u to be x, because arctan of tan x is x. Thus, x is equal to arctan of u, and our whole thing here simplifies to arctan of u over u du, integrated with respect to u. So now what should we do here now? If you try to solve this integral, you're gonna again go and reach a new problem. But what I'm gonna do is I'm gonna expand arctan of u using the Maclaurin series. Arctan of u is sum from k equals 0 to infinity of negative 1 to the power of k over 2k plus 1 u to the 2k plus 1. Now, what I'm going to do here, I'm not going to substitute, I'm not going to write the summation notation to make our work simpler, but the k index is summed over, to just keep that in mind. So now it's going to be 2 over pi from 0 to pi over 4 of oops, I should have switched the bounds here from 0 to 1 again, sorry. Negative 1 to k over 2k plus 1, it's going to be the sum from k equals 0 to infinity of negative 1 to the power of k over 2k plus 1 u to the 2k du. I said that I'm not going to write this summation notation here, so the 2 over pi is going to go out. The negative 1 to the k over 2k plus 1 is going to also go out, and we're left with integral from 0 to 1 of u to the 2k du. Now, you can obviously integrate this function with the reverse power rule. Negative 1 to the k over 2k plus 1, u to the 2k plus 1 over 2k plus 1 from 0 to 1. And if you do that calculation, you're going to be left with the expression of 2 over pi negative 1 to the k over 2k plus 1. And I'm going to write it in summation notation to this is going to be 2k plus 1 squared. So if I take out the 2 over pi, which is a constant in our sum here, it's negative 1 to the k over 2k plus 1 squared. This thing here is known as the Catalan's constant, which has a value of approximately 0.95. I don't remember the exact value, but this series is convergent. So I'm going to call this series G, and our final result is going to be 2 over pi G. Thus, the integral that we were looking for first, from 0 to infinity of root x minus 1 over x plus 1 squared ln x, ex is 2 over pi G, which is approximately 0.5 something, I don't remember. So this is our final integral that we obtained from this analysis, this long tedious analysis with gamma and beta functions. So let me know if you have any questions in the comments. I will read all the comments, every single comment. And if you like this video, please like and subscribe, and I will see you next video.